You're live.
I'm live. Okay, so I need to be very careful with what I say because now the things are recorded. Plus, there's my boss sitting there, so I have to be very careful. So I will lay low on the jokes today. I hope it's still funny enough for you. Functional programming in Java with or without streams. So this is something that just pop up. I'll tell you more about how I come to do this example. And at some point, I felt it was interesting enough to share my experience with this. And since they were looking for a speaker, I said, hey, why not? I'll do that. In case you're interested, you don't need to take pictures or everything. Code-wise, everything is on the GitHub public repository. If you want to see the Java code, that will be in the slides. Okay, so it's all there. It's mostly code in those slides and me talking about it. So, starting point is functional programming in Java. Can we do functional programming in Java? So this is something that's been discussed a lot, and typically the most common answer is yes, why not? We can do functional programming in Java. And the sort of things I'm sure we've all seen is little examples like this. So Java has streams which implement the standard higher order methods, and then a nice syntax for lambda expressions so you can feed those higher order methods with functions. So here's an example. I have a list of numbers. Here I want to create a list of their squares. I can do it by creating a stream out of my numbers and then using this map function that applies a function to all the elements of my list to create a list of the squares, right? So I'm passing to this map function a function that square things, that goes from a number to the square of that number. That gives me a stream of those squares, and then I convert it back into a list, and I get the list 1, 9, 49, 81. Okay. So a very typical use of a higher order method. So map is known as a higher order method that takes as argument another function to be applied inside the list. Another example, if I have a list of strings and I want to keep only the non-empty strings, I can filter out the blank strings by, again, going into the word of streams. In Java, you have to do everything with streams, and then using a filter, higher order function, to get rid of all the strings that are not blank. Sorry, to keep all the strings that are not blank, getting rid of the strings that are blank, and then going back into a list at the end, list of strings. And this is nice. Here's a more complicated example of mixing both the filter and the map. So let's say I have a list of lines. I want to know the length of the shortest non-blank line. Okay, so I have a list of lines. I want the length of the shortest line, but not counting empty lines. So I can do a filter to get rid of the empty lines, a map to map lines to their length to get a stream of numbers, and then applying a minimal operator to get the smallest length with a default to 0 in case my stream is empty and doesn't have a well-defined minimum. And that's typical functional programming in Java. I have nothing against it. I actually like it. I find the biggest argument for me of this kind of code, which I tell students, is legibility. I find that easier to read than the corresponding imperative code, right? So if you think how you're going to do that in an imperative style, you're going to have a loop with a couple of ifs in it. But a loop with 2 ifs can do all sorts of things. So just by looking at a loop with 2 ifs, you have no idea what it's doing. You have to dig into the loop and the ifs to know what's happening. Here, without digging anywhere, you know, okay, there's some filtering, some mapping, and it's a minimum computation. Right? So you get a lot more information at a glance than with the corresponding imperative code. So that's nice and well. But my question for today is, okay, is that all there is to it? Okay, is that functional programming? I'm not going to try to define functional programming, but can we do something else? Can we do more? So what happens if you try to do something that are a little more advanced in functional programming and stay within Java? Okay. So my case study for this, exploring this, is going to be, it's going to be small. It's a Sudoku solver. Sudoku is a classic kind of programming we do in school, make students implement Sudoku because it's a good example of a branching with backtracking and recursion. So we all know what Sudoku puzzles are. You have a partially filled grid of numbers, and you need to put all the numbers from 1 to 9 in the empty squares, such that there is no duplicate in any row, column, or major square, those 3 by 3 squares there. Right? So all the numbers have to be different in the 3 by 3 squares and in all the columns and in all the rows. So how can you solve a Sudoku puzzle? So that is really small for me. One way to solve that is you pick an empty location, like this one here, and you calculate what numbers could possibly go there. Right? So if we look at this, it's hard for me to see because my iPad is small. As this pot, you cannot have 9, 1, 6, or 4 because it's already in this column. You cannot have 5 or 2 because it's in the row. And you cannot have 9, 8, or 1 because it's in the same 3 by 3 square. So all that's left for that position is either 3 or 7. Okay, so those are the two numbers that can go there. You don't know which one will solve your puzzle. So you can try one. You can put a 3 in this square and then try to solve this new Sudoku puzzle. Okay, this one is an easier puzzle because it has fewer empty squares. So you can rely on recursion to solve that for free. And then if that works, you're all set. If it doesn't work, if this puzzle has no solution, then this branch has failed. You're going to try to instead put a 7 in the empty square and try to solve that one. And if this one doesn't work, well, that's it. There is no third possibility. This puzzle you started from cannot be done. Okay? So it's a branching thing, right? So every time you have a possibility of numbers, so like this where am I? This square has 3 possibilities, 5, 7, 8. You have 3 possible branches to explore, and then it's backtracking in the sense that if a branch doesn't work, you come back and you try the next one. And if all your branches fail, well, it fails. Okay? So recursion, branching, and backtracking. That's what's in this algorithm.
Is this like the new 8 queens problem?
Yeah, it's more interesting to me than the 8 queens, but it's been used a lot. But I'm going to make it a little more interesting because I'm lazy like you. So I'm going to bring some laziness in it.
No AI?
No AI. I can say a few things about AI at the end, but you don't want to hear me about AI.
It'll solve the problem, but the solution will have 3 thumbs.
Now I don't know what I was talking about.
Backtracking.
Backtracking.
Branching.
Branching. And recursion. Yeah, something I wanted to say, but I forgot. So anyway, let's start with a simple Java implementation of this. And then I'll go into a sort of a more advanced implementation that relies on other functional programming patterns. So I'm implementing a class, my simple Sudoku. I'm representing a grid as an array of 81 integers. Right? So that's the state of my grid. 0 represent empty squares, and then I have all my numbers 1 through 9 in my array. And then I'm going to make my grids immutable. So when you put a number into the grid, you get a new grid. Okay, the reason I'm doing this, it makes backtracking easier. So if some branch does some computation, I still have my original grid to do the other branches. The alternative is to undo what a branch has done before branching into the other branch, and that's going to get more difficult with my other implementation. So to avoid those problems, I keep my grids immutable. So when you update a grid, when you put a number, what's happening, you call this updated method, which gives you a new grid. Okay, so the original grid doesn't change. You clone everything. I'm copying my array, putting the new value into the array, wrapping it again into a simple Sudoku. Okay, so I can set a number, get a new grid that creates one branch. That's the function that creates branches in my search. Once I have that, I need to calculate how many branches I have and what the branches are. So I call that the possibles function, but calculate all the possible numbers that can go to a square. Right? So like I said, eliminating all the numbers that already appear in a row, column, or 3 by 3 square. Those are eliminated. The remaining numbers are my possible branches. So that's the code to do this. I'm returning them as a little bit set of numbers. I start from a full set, so all the numbers from 1 through 9, and then I eliminate all the numbers that cannot go. Okay, so I create a bit set with all the numbers, and then I do a loop, or for every position I that conflicts with the index that I'm looking at, right? So that means I that is in the same column, same row, or same 3 by 3 square as the index. I need to remove from the set the value that's at position I. So this value is not a possible one anymore because it's already used in the row or column or square of that grid. Okay, so I do that for all the positions, and I return a set of possible numbers. If this set is empty, that's it. I have failed. There is no number that can go into the square. This conflict function is over there, right? So it just tells me if 2 indices in my array correspond to the same row, same column, or same 3 by 3 square. So I have a way to enumerate my branches. That's the possibles functions, and I have a way to dive into a branch. That's my updated function. So with that in place, I can implement my recursive solving method. Okay? So my method solve will return a full grid as an option because a puzzle may not have a solution. So I need a way to return no grid. And as we all know, we don't use null pointers to do these sort of things because that's dangerous. We use options. And the way it works, I'm looking for an empty square. Okay. This function returns -1 when the grid is full. There's no empty square. So if the grid is full, that's it. It has been solved. Right? I've put all the numbers everywhere. There are no empty squares left. I just return the grid itself as the solution inside an option. So that's my success return. If I get an actual index, then what I do is I calculate the possible values that could go into that index. Those are my branches, 2 branches, 3 branches. And then I do a loop over those branches. This is the ugly code to do a loop over a bit set. So I'm going over all the numbers into the bit set. And for each branch, what I do is I create a new grid by updating, putting the number in this place, and I'm making a recursive call to solve. Right? So after I put a number, try to solve it. If this comes back with a solution, I'm done. Right? So if this comes back and a non-empty option, I just return that. I found my solution. If it doesn't work, so if after I put the number 3, I branch into my recursion and it comes back saying it cannot be done, well, then number 3 was a mistake. I need to put the number 7, right? So then if it doesn't work, if the solution comes back empty, we go back at the beginning of the loop and we do the next branch. If we run out of branches, we tried all the branches and none of them worked, well, that's it. We could not do it. We return an empty option. That's the failure case of my search. Okay, so going and backtracking. So find best empty. I don't have the code here. It's just to find an empty square. It's called best empty because I'm looking for a square with minimum branching. I want to minimize the branching at the top of my tree. And then the rest I think I've already talked about. Okay. So what I'm going to do now is this. Right? Keep an eye on this. This is the computation that's doing the solving of the Sudoku. That's the same computation I'm going to do in all sorts of different flavors, but it's always the same computation is going to take place. That's my search algorithm implemented in different ways using different parts of the language, okay? But that's always that same one. Enumerate your branches. For each branch, make recursive calls and find a branch that works. So that's the function that gives me a solution to the Sudoku, but maybe I would like to know all the solutions. If the solutions are not unique, maybe I'm interested in finding all the ways to solve that puzzle. So what do I need to change for my code for this? It's almost the same, right? I look for an empty square. If there is no empty square, that's it. I have a solution. I put it into a list, right? So the difference is instead of producing an option, I'm going to produce a list at the end, a list with all the solutions. If I find an empty square, I enumerate the possibles. I do my loop over all the possible numbers that can go into that square. And for each branch, I create a new grid with that number in it. And I add all the solutions of that new grid to my list. At the end, return that list. So it's very much the same code, right? If you think about it, the only difference is with the previous one has this if here, right? There is an early return. If I find the solution, get out of it, I'm done. Here, the if is gone, right? So even if I'm adding some solutions here by using this number P, I'm still going to go into the next branch to add more solutions. So I'm adding all the solutions that all the branches produce. So the code is very similar to the previous one. It's arguably simpler than the previous one because it doesn't have that if to exit the loop at the first solution. It's kind of more regular code and doesn't have to deal with the options. And that's a very common case in those searches, that the code for all the solutions is actually simpler than the code for a single solution. Okay, but at least it's very, very similar. Same algorithm without the early return in the loop. Okay. Now, Sudoku puzzles, they're supposed to have a unique solution, the ones that are in the newspapers. And so if you start generating puzzles and things like that, you may be interested in knowing that the solution is unique or not, right? So that's another function I want to implement. Tell me if a solution is unique. So it's, again, very similar, right? What I'm going to do is I'm going to search for solutions. But the difference with the function that calculates all the solutions is as soon as I find a second solution, I know it's not unique, and I can stop, right? So the only part that's changing is I'm bringing back this if inside the loop, and if at some point my list of solutions has more than one value, that's it, we're done. We can return the list, and then my solution is unique. Public method is just testing that the list we get at the end has length 1. Okay, so I don't have to calculate the third, fourth, and so on solutions. As soon as I see 2, I know it's not unique. Okay, so I have 3 variants of my solving: find a solution, any solution, find all the solutions, and find if the solution is unique by looking for at least 2 solutions. okay? All useful methods for my Sudoku application. And it's exactly the same algorithm, and it's exactly the same code, okay? So my problem is I don't want this code duplication, okay? If there is one thing I'm trying to teach students is don't repeat yourself. You do not want to duplicate code. It might be short enough here from the Sudoku, but if it's more complicated, I don't want to have to maintain 3 variants of my code. Yes?
So how many times do you have to tell your students not to repeat themselves?
I have to repeat myself a lot, yeah. So that's bugging me, this code duplication, right? I've really written the same program 3 times with slight variants, okay? So I want to avoid that. So that's one of my goals, avoid code duplication. However, I don't want to do this. That's why there's the don't do this. I could be tempted to say, okay, the function that calculates all the solutions, that's the most powerful. If I have all the solutions, I have a solution, any one from the list, and I also know if the solution is unique or not, right? So I could implement only the all the solutions method, and then implement the other 2 in terms of that one, right? So if I want to know a solution, I'm just going to calculate all the solutions and then extract one. It's a little annoying in Java. I'm returning my solutions as a set. There is no function in Java to get one value out of a set. So the trick that I'm using all the time is just I start a loop and I return it with the first value. You create an iterator and just return the first value. But anyway, I'm calculating all the solutions and then grabbing the first one and returning it. Right? If I want to know if the solution is unique, same thing. I can calculate all the solutions and then just check that the size of that list is exactly 1. The reason I don't like that, functionally it's going to work, it's an issue of performance. If I only want one solution, I don't want to waste my time calculating all the solutions. If I only want to know if a solution is unique, I also don't want to calculate all the solutions. Okay, think of an extreme case. You feed an empty grid with no numbers in it. There are lots and lots of solutions to that one. Okay, I want my code to find a solution very easily and to tell me it's not unique very easily. I don't want to start to enumerate all the possible ways of filling that grid. So this code is too inefficient. It avoids duplication, but it's too inefficient. And it's inefficient in 2 ways, right? That's the first way that I talked about, is that I'm calculating things that I don't need. More solutions than is needed. The second inefficiency is that I tend to recalculate things across methods. So for instance, I solve the puzzle, I get a solution, and now I'm curious, okay, is it unique? So now I'm calling my is unique, but I'm restarting the work from scratch, right? I'm recalculating all the solutions. So not only I'm calculating too much, but I'm calculating too much multiple times. Okay, so I want to avoid that. I want to avoid my code duplication, but I want to keep my performance and reuse of solutions that I've already calculated. So, new design. I'm switching from my simple Sudoku to a class I call Memo Sudoku. That's the one that's going to be interesting. All this, I have 30 minutes of throat clearing before I get into the gist of it. I'm going to do a few little optimizations. I'm going to store the set of possible values with the grid, so I don't have to recalculate all the time. So if you think about it, if you've calculated that there are only 3 or 4 values that can go into that square, after you put a number elsewhere, what you're going to do potentially is shrink that set, right? So now I put a 5 somewhere, so 5 cannot be in some of those sets anymore. So I can calculate the set of possible numbers of my children grids from the parent more efficiently than recalculating them from scratch. So I'm going to store my sets of possible numbers for all the squares, all the empty squares in the grid, and then reduce them every time I go through a branch. That's a minor thing. Because of that, because I'm going to store 81 sets, I want my sets to be fast and small, because remember, I clone my grids to make them immutable, so I don't want to have to copy 81-bit sets. So I'm going to do my own implementation of small sets. Okay, my sets contains at most 9 numbers, so the bits of a single integer are good enough to implement that set. So I'm going to write a little bit of code to have small sets represented as an int. Another thing I can slightly optimize is instead of going through all the positions in the grid and finding which one conflict with the positions that conflict with a certain location in the grid they're always the same for all the Sudoku grids, right? So if you pick an index, all the indices that represent the same column, same row, same square, they are a fixed thing. That doesn't change. It's not based on the numbers that are in the grid. So I can calculate that once and for all. So I can go more easily. Instead of iterating over the entire grid, I can iterate over only the places that conflict with the current index. Okay. So those 3 things are just like small optimization, storing things, avoiding recalculation of things. The big one is there. That's the one I want to talk about, because that's the standard thing in functional programming, is to add lazy evaluation and memoization to my solving method. Right? So the idea is to implement only one searching method that finds all the solutions, but that returns the solutions in a lazily evaluated structure. So it returns the solutions without computing them. So conceptually, I have something that contains all the solutions, but they will be calculated as I need them on demand if I start digging from that structure. So that's lazy evaluation. Evaluate things as you need them. And then the second thing I want to apply is memoization, which is just a fancy word for caching. I want to store the things that I've calculated already, right? So every time a solution is calculated, I want to store that. So if I've already solved, I already have one solution. Now, if I want to find if there is a second, I'm continuing from there. I don't want to recalculate the first one because I already have it, okay? So those two things are used quite a bit in functional programming, lazy evaluation especially, and memoization. So I want to bring lazy evaluation and memoization to my Sudoku so that I get my triple goal, which is no code duplication, calculate as little as I need, depending on my needs, if I want to solve one or solve all or find unicity, and do not recalculate a solution multiple times. Yes?
So that's memoization only for full solutions, not for the...
For full solutions, yeah. No, not for the intermediate, no.
Okay.
No. I don't need it for the partial one for this one. Yeah. And once I have that, I will implement my 3 public methods in terms of it. Okay? So, quickly again, the first 3 bullet points, that's not super important, but I still have them because I'll talk a little bit at the end on how I implemented some of that. So this is calculating the pairs of conflicting indices once and for all, so into a static array. Position I and position J are in the same column, same row, same 3 by 3 square. I can store that into a static array once and for all my Sudoku grids. So I create this conflict with array. And so, for instance, conflict with of 4 is this list of numbers which represent all the positions in the grid that are in the same row, same column, same 3 by 3 square as position 4. So this is calculated once and for all. Small sets as bit operations on a single integer. Okay, so I've implemented a small int set class where sets of numbers are implemented as an int. So the empty set is just 0, no bits set. And then if you want to remove a number, you put a 0, you shift it into the right position, you do the mask, and you clear a bit that way. If you want to test if a bit is set to see if something is in the set and so forth, the number of bits is the cardinality of your set. I can implement all the set operations that I need quickly on a single integer. Okay, this way I can store small sets with my grid. My possible sets, so I'm going to calculate them at the beginning when I start my search, and then every time I branch, I'm just going to reduce my existing sets based on the number that's been added instead of recalculating them from scratch. So this code's a little bit complicated because once I decide to be lazy, I really want to be lazy, so I want to calculate as little as possible. So when you create a grid, I don't even want to calculate the possible sets. So if I create a grid just to print it, I'm not solving it, I don't care. The moment I start solving, I want to start to calculate those sets. So there are 2 cases. The top grid, I'm going to have to calculate the sets from scratch. And then all the other grids, they are obtained by updating their parent sets. Okay. So that's why I have this bizarre code. You may have known sets because you've been created as a child or not. And if you don't, then you're going to have to generate all the possibles. Okay. So I'm looking at this possibles fields, which is null initially, and then the first time I need it, I check to see do we already have them because they were created when the grid was created, or do we need to calculate them, which is only the one time when I start my search. The updated method changes also a little bit, right? So I clone not only my array of numbers, my grid, I also clone my sets. So this is, it's hard to read, but this possibles, what it returns is an array of sets. Right, each integer is a set. So I'm cloning all my sets, the possible numbers for all the values. So I'm setting the new value when I do update it, and then I do this thing for every position j that conflicts with the position I just set. I need to remove from the sets of this, the possible sets of that position, the value I just set, right? So if at position 4, I add the number 5, then for all those numbers that are positions that conflict with 4, they cannot have the number 5 anymore, so I remove them from their set. Okay, so the sets are calculated by shrinking a little bit from the parent. Okay, now laziness. That's what I want to talk about, right? I'm talking about streams in my title, so it's time to begin the streams. So if you remember those other presentations you've seen on functional programming in Java, one thing that's emphasized is that those streams, those Java streams are lazy. They are lazily evaluated, which is one thing I need. So what does that mean? So going back to my example of squaring numbers, right? So I have a list of numbers. I want to square them, but this time instead of just squaring them, I'm using a method, a function that is a verbose square. It squares the number, but also prints a little something so I can see that it is happening. Okay, just to keep track of what's running and not running. And then I'm interested in finding a large square, so I want to keep of those squares only the ones that are larger than 20. And then I'm grabbing that first square. So what's happening is that when you create this stream of squares, nothing is printing, nothing is happening, right? So passing this function, the map function here does not invoke the verbose square. It just creates a new stream, but does not calculate anything yet. Okay. Same thing with filter. When I filter and keep only all the squares larger than 20, nothing is taking place, no computation. Only when at the end I say, okay, give me the first square larger than 20, then the computation takes place. And you can see at this point, you're going to see a message that says we have to calculate the square of 1, the square of 3, and the square of 7. Right? So the square of 1, 3, and 7 are only calculated when I need them on demand. And the square of 9 is never calculated because I never need it. The square of 7 gives me something larger than 20, so I'm done. Okay? So the streams are lazily evaluated. They calculate things on demand and no more than what's needed. So that looks good for me. I would like to create a stream of solutions to my Sudoku puzzle. So I get them on demand and do not calculate the ones I don't need. So how I'm going to do this? I'm going to create a stream of possible values, right? So remember, I calculate the possible values right now as a set, my small set. I want to be able to generate a stream of values from that set. So I can create a stream of branches, right? Because those streams have lazy evaluation. So that's easy enough to do. There's a little code here to create an int stream out of a set, just going through all the bits. You go from the lowest bit, you clear the lowest bit, you add the lowest bit, you clear the lowest bit until all the bits are cleared. You have put all your numbers into the stream. Okay. So I can have a stream of my sets. So that lets me do things like this. Instead of going through a list, I can create a set, like a set of possible numbers. 1, 3, 7, 9 are my possible numbers, and I can do the same thing. Do a map on my stream, do a filter on my stream, nothing is calculated, right? It's all, I get all the laziness of the Java streams. And then only when I call find first, I get the behavior of squaring the first 3 numbers to find the first one that's larger than 20. Okay? So a stream of branches, so I can have the lazy evaluation of my solutions. With this in place, this is the hard slide for me to explain. That's the solving method. So the solving method is going to work in terms of streams now, right? So you can see it's going to produce a stream of solution, a stream of Sudoku, full Sudoku grids. So it starts the same as the one that used the loop. So look for an empty square. If there is no empty square, then that's it. There is only one solution. Return a stream that only contains that grid. Otherwise, we have to go over all the branches. And for each branch, calculate the stream of solutions that can be produced after that number has been put in. Does that make sense, right? So I put a number. After this number is in, there is a stream of possible solutions. So that's what I'm doing here. I'm calculating the possible numbers for this index, and I'm making a stream out of it. And then for each value p, each possible number in that stream, I'm doing an updated grid with p set in that grid, and I'm solving it recursively, getting the stream after I branch into this branch. And then the fancy operation there that puts everything together is called flat map. Okay, so I'll talk about flat map in a minute, but I want to make sure we understand this flat map is actually implementing this loop that we had before, right? It's going to go over all the possible numbers, and for each number, calculate a stream of solutions and put all those solutions together. So I'm creating a stream of all my solutions. And the reason I want to do that is because calculating a stream of solutions is not going to solve anything until I start digging from that stream. And then if I want one, I take one. If I want all of them, I take all of them. Okay? So flat map is the big guy of functional programming, very important operator, both for theoretical reasons. So if you look at the category theory roots of functional programming, they talk about something called monads. You may have seen this fancy word. That's something with a flat map. But it's also important from a practical standpoint. It's a very useful higher order function. In particular, you can re-implement map and filter in terms of flat map. So flat map is an important one. It's also one that's a little harder to understand. So with my students, I tend to say map, filter, that's easy. Flat map, we're going to have to slow down a bit. I'm trying to illustrate flat map here. So flat map, it's map plus flattening. Okay, that's what the name is from. Think of a map plus a flattening step. So say like if you have a function that transforms an input into a collection, so into a stream. For each input, there is a stream of values. And you have a stream of inputs. If you were to use map on the stream of input, you would get all the outputs for A, so that would be one stream, and then all the outputs for B, that'd be another stream, and all the outputs for C, another stream. So you're going to get a stream of stream. Okay? Flat map makes that little difference that all those things are flattened into a single stream. So it's very easy to understand conceptually what it's doing. It's a little harder to get used to using it. So in Sudoku, that's exactly what I need. The function f is the function, the input is a branch, a possible number. The output is a stream of solutions after you've put that number in the grid. Right? So I have a function from a value to a stream. That's my solving function. And then flat map takes a stream of branches. So I take my set of values, I make it a stream. I have a stream of branches, and I go into a stream of solutions. Right? So like here, I have a stream of inputs. I have a function that transforms each input into a stream, and flat map gives me a stream of the outputs. So I have a stream of possible numbers, a function that for each possible number gives me a stream of solutions, and flat map gives me all the solutions in a single stream. Okay? So once I have that, so this is really, right, the method that does everything. It calculates a stream of all the solutions with this fancy flat map. Once I have that, I can implement my 3 public methods. So if I only want one solution, I'm going to call find first on that stream. So calculate the stream, and then ask for the first element of the stream. So calling solve stream is not going to compute any solutions, right? Only when I call find first on the stream, then the computation is going to start digging into that stream until it gives me a value. It's going to traverse enough of my computation tree to give me the first value and stop right there. The rest will not be evaluated, same way as my squares, my numbers were not squared in my little example. If I want all of them, then I use a different operation, collect. I can collect all the values of the stream into a set. Then that's going to force the evaluation of everything in the stream. So I'm going to calculate my entire tree and with all my, my solutions. If I only want to know if a solution is unique, I can create a stream of solutions and then limit it to 2 values. So that's a stream of at most 2 solutions, a stream of the first 2 solutions if you want, and then see how many solutions are in that stream. If there is exactly 1, then the solution is unique. If there is 2, then it's not unique. But it will not calculate more than 2, right? Because of this limit of 2, we will not evaluate the rest of the stream after that. So I have the lazy evaluation to give me exactly what is necessary, right? I do not calculate more than I need. My solve method calculates only 1 solution and not the others. My solve all calculates all of them. And my unicity method calculates only the first 2 and then stops to tell me it's not unique. So that's what I wanted to achieve. I get the performance of my handwritten code without the code duplication, right? That's the beauty of it. Be careful if you try this. Didn't work when I first started. I was using Java 21, which is the current LTS. It turns out there's a bug in the implementation of flat map on streams. And so I was scratching my head a lot because things were being evaluated that should not be. That's why the hair is gone. It turns out this bug was fixed in Java 23. So I had to switch to a fairly recent Java. We did everything in Java 24 because up to 23, there's still a bug in the streams. But now it works. Okay. So what does not work? What I do not have, so I have 2 of my 3 bullets, right? I have no code duplication, and I only evaluate as many solutions as I need. What I do not have is the memoization. Right? So if I call, say, solve, okay, I have a solution. Now, if I want to say, is this solution unique? I'm going to call my solution is unique, which is going to recalculate the first solution and then look for a second one. I would like to reuse the first solution that I already have and only look for a second one. Okay, so I'm still missing that. Why is this a bit tricky? So these methods that I use on the stream, right, the ones that trigger the computation, right, so the stream is all lazily sitting there, not evaluated, and then you call an operation that triggers the evaluation of parts of the stream. Those are called in Java terminal operations. And what they do is that they destroy the stream. They give you information out of your stream, but after you've called a terminal operation on the Java stream, you cannot use the stream anymore. It's gone. So after you call find first, right? So I have a stream and unevaluated solutions. That's nice. I call find first to find the first. Okay. Now I would like to continue. Okay, give me the second one. I cannot do that because the stream is gone. Right. So those terminal operations destroy the stream, and my stream cannot be reused. And so I don't like that. I would like to have a method to continue where the previous method left off. Right. So if I already calculated the first solution and now I want more, let's continue to calculate more. If I already calculated 2 and I know we are not unique and I want all the others, let's continue to calculate from there. So I would like to store the solutions as they are being calculated by the stream, right? As I dig values out of my stream, I would like to keep them. That's the memoization aspect. So how am I going to do that? My idea was to use iterators, because if I have an iterator, I will be able to store things as I get them out of the iterator. And as it turns out, the stream class in Java has an iterator method. So I can get an iterator out of a stream. So it would look something like this, right? I could calculate a stream of all my solutions. No computation taking place yet. I have just my stream. Calculate an iterator, get an iterator from my stream. And then the first time I call next on that iterator, there's going to trigger enough computation to give me the first solution. Now, if I want more, I call next again on the same iterator, and I'm getting the second solution out of the stream. So trigger enough computation to give me another one. If I want more, I call next again. If I want all of them, I keep calling next on my iterator until I've put them all into a set. So in theory, that should work. In practice, it didn't, which is why, again, I was losing so much hair. So for a different reason, it turns out that when you call next on the iterator that comes from a stream, it evaluates a lot more than the first value. I was hoping that just calling next would do like find first, give me the first value of the stream and stop there. It does a lot more computation than this. The stream API description for the iterator method, they say this is provided as an escape hatch. So this is not kind of a normal use of streams. You're supposed to do everything within streams in the world of streams. They do have an iterator method, but it's a little shaky. And so when I dug a little more and got in touch eventually with Klong, who seems to be maintaining the code for the streams and who actually fixed the bug in Java 23 that they had on FlatMap, what he told me is that the streams are implemented as a push-based style, and an iterator is really at its core a pull mechanism. You pull out from the iterator. And so creating a pull-style iterator out of a push-based stream has, like he says, limitations. It just doesn't work very well.
Polite way of saying don't do it.
Don't do it. So I think what's happening is that internally, to get that iterator, they need to buffer enough things to then give you an iterator out of that. So single call to next calculates a lot more than I wanted to. So that's where things fell apart. That's actually when I started to think, hey, that might be an interesting talk for those Java guys because it doesn't work as well as I thought it would. So what do I do now? So I can get my lazy evaluation from the streams, but then I cannot memorize them, at least not easily. I haven't found another way without it. How coroutines would help me? Switch to AI, ask AI to do it. Make you do it in your spare time. Yeah, I thought of different ways to do it, but in the end, what I would like to do is get an iterator of solutions because I know how to memorize an iterator. That's easy to store things as they come out of the iterator. So I want to have an iterator of solutions without going through streams because streams won't give me a good iterator, right? So I want to create my iterator of solutions myself. Because iterators are nice too. They also have this lazy evaluation property, right? You create an iterator until you call next. Not much is happening. But then I can call next, 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 and get the values one at a time, which I cannot do with the stream. So let's calculate an iterator of solutions from scratch, bypassing the streams. So what does that involve? I remember my stream of solutions comes from creating a stream of branches and then using FlatMap on those branches with a recursive call. So let's do the same thing. I can just create an iterator of branches, and then do a flat map on that iterator, right? So in the same way that if each branch gives me a stream of solutions, flat map will give me a whole stream of all the solutions. If each branch gives me an iterator of solution and I have a flat map on my iterator, then I will get an iterator of all the solutions. It's very much the same thing. So what I'm missing is those two parts, right? I need to create an iterator out of my small sets. And then I need to somehow implement flat map on iterators because the Java iterators don't have it. Okay. Once I have those two parts, I will have a function that produces an iterator of solutions, and then the rest of it will be easy. So let's do that. Small set iterators, that's very easy. This is the code I use to create a stream of values, right? Grab the lowest bit, clear it, grab the next lowest bit, clear it. I can do exactly the same thing in an iterator. So that's not a big deal, right? So inside the next method, you look at the lowest bit, which is the number of trailing zeros, and then use this little arithmetic trick to clear it. And you do that every time you call next. You get one value out of your set, and the set, the iterator is exhausted when the set becomes empty and the number is 0. Okay, so it's very much the same code that creates a stream of numbers out of my set can create an iterator out of my set. Flat map is a little more work, so now I need a way to flat map iterators. Okay, so this is implemented in my flat map class. So given an iterator of A and a function from A to iterator of B, create an iterator of B. That's the signature of a flat map, right? So I have a collections of type A. I have a function that for each A gives me a bunch of B's, and I'm creating a whole bunch of B's out of it. So I have an iterator of A, a function from A to iterator of B. Flat map gives me an iterator of B. So that's what I want to implement. So that's not too difficult. The way I'm doing it, I'm storing the function that is given, the iterator of A's, and then I have an iterator of B that I get by applying the function successively on each value A that comes from the original iterator. And I keep all this private, and it's being used through the flat map function that was in previous code. So I have a static flat map function. You give it the iterator of A, you give it the function from A to iterator of B, and it gives you back an iterator of B. There is this ugly signature here. I wrote it that way because that's the way it's supposed to be written in Java, but you can think of it as this. It's a function from A to iterator of B. In another language, I would just write function from A to iterator of B. If I were in Scala or in Kotlin, I could because I have variance, covariance, and contravariance. I don't have that in Java. It's one of the things Java doesn't have. And so you have to deal with those type bounds to make the contravariance here and the covariance here and there. Last time I was here, I talked about Scala and Kotlin. Unfortunately, I had something like 55 slides, so we had to be kicked out of the room after dark before I got to covariance and contravariance. So I think someday I'll come back with just that. I'll talk just about covariance and contravariance. Because it's important in Java, because you have to get around the problem, the fact that Java doesn't have it. The more modern C#, Kotlin, Scala, they have it. But Java is the old guy that doesn't have it, and so you have to know how to handle that. At any rate, this is a complicated way of saying function from A to iterator of B. So how is this iterator implemented? So what I do is I grab the next A out of the original iterator, apply the function to it, that gives me an iterator of B. And then I keep digging the B values out of that iterator until it becomes empty, right? So when this iterator comes empty, I go back and grab the next value of type A, pass it to the function, get a new iterator of B. So every time I have an A, pass it to F. F gives me a bunch of B's. I return them one by one. When I run out, go to the next A, apply the function again, get a bunch of B's, and so forth. This implementation is not very good because if you start nesting calls to flat map, which is what I'm doing in my recursive search, it uses a lot of execution stacks. So what's happening is that when I apply F to a value, here I'm getting an iterator, but that iterator is itself going to be one of my flat map iterators, which means when I do current.hasNext, I'm re-entering hasNext here. So I'm starting to nest the calls to hasNext based on how much nesting there is in my flat maps. So a good implementation of flat map would avoid that. So you could nest flat map arbitrarily and not run out of execution stack. I tried to write it and I couldn't. That's another thing I need to ask the AI to do because it turned out to be tricky. The code was growing and growing and it was still not working. And after a while, I said, okay, first of all, if I get 15 pages of code, I cannot show that and nobody cares. So why am I wasting my time? And secondly, we're talking about Sudoku. The worst case is the completely empty grid. I'm going to nest 81 calls to flat map. 81 is okay, right? The execution stack can tell that. But I cannot nest 100,000 calls, for instance. A library function would probably try to do that.
Make the stack bigger.
Make the stack bigger. That's another approach.
There's
Yeah.
an option for that.
Bigger hardware.
As long as you only have one thread, that's not too bad. Okay, but that does the job, at least for my Sudoku problem. I can flat map iterators. So now everything is in place, right? Oh no, memorization. I still need to memorize my iterator. So that's not a big deal. If you have an iterator of A values, I can keep into a list, a cache, all the A values that come out of the iterator. Every time next produces a value, put it into the list so I can have them for later, right? So if you look at the code for next, what we keep track of is how many values have gone out of the iterator. And as long as we are below the cache size, we just get them from the cache, right, directly from the list. Once we go beyond the cache size, we have to get them from the iterator itself, put them into the cache, and then return them. Okay, so it's just a little wrapper around my next method, around the next method of this iterator. Every time something comes out of it, put it into the list for later. So I've now implemented my lazily evaluated list with memorization. Right? Given an iterator, it will be evaluated lazily every time you call next, and it will also be stored for memorization if you want them later. So in the end, this is what my solving method looks like, right? So that's the one we had before. I do an iterator of my sets. I use my new flat map on the iterator to calculate all my solutions. And then I just want to store them. And again, I want to do as little as possible because I'm lazy. So if you create a grid, I don't want to trigger any computation whatsoever. So I keep this null when the grid is created. And only when you need it, then it's going to be calculated this way. So I just want to delay the evaluation of this code, even though there is not much here, right? There is the code that creates an iterator of solutions that does not compute much, and then wraps it into a memorizer, which also is very little. There is a little bit of code happening here because of the recursion, but very little. At any rate, I just want to delay this code for as long as possible. So that's why I have this null field that with a delayed initialization to it. Once I have this, I can again implement my 3 public solving methods in terms of that iterator, right? So if I want one solution, I grab an iterator out of my memorized collection of solutions, my lazily memorized collection of solutions. If that iterator has a value, then grab it, return it as an option. So that will trigger computation of exactly one solution. If I want all the solutions, then I grab an iterator and then I say dump everything from that iterator into a new set. Then I get all the solutions that will trigger evaluation of everything. If I want to know if a solution is unique, I grab my iterator, and then if it's empty right there, that means there was no solution for this puzzle, so it's not unique. I return false. Otherwise, I skip the first solution and then I ask, is there another one? If there is another one, then it's not unique. And the computation stops there without digging more from the iterator and therefore digging more into my solving method. Okay, so I'm getting the 3 things I wanted. Okay? I don't compute things until I need them. No computation takes place until you start querying solve all solutions or solution is unique. I do not recompute things. So if I've called solve, I already have a solution, and now I call solution is unique. We're going to continue, try to get the second solution, but we already have the first one. And I have no code duplication. Okay, so I've achieved my goals. However, I have not used streams. Streams got, it looked good because of the lazy evaluation that's already built in, but I could not memorize them. I didn't find a way to memorize them without going through iterators, and their iterators are broken. So I skipped the stream. So what, no stream? I did use stream in other places, so I think it's interesting to see that. In other places, I try to keep using the streams anyway. So if you remember, there's this conflict with my array of pairs of indices that conflict. So if 2 positions that are in the same row, same column, or same major square. I calculated that with an iterator. So I'm saying for every position I, what you do is you start from all the indices, and then you filter them to keep only those position J that conflict with I. So that creates the list of all the indices that are in the same row, same column, same 3x3 square, and then dump the stream into an array at the end. So I'm still using a filter on the stream to calculate that. This one's a little harder to read if you're new to functional programming, but that's how I generate my possible sets from the top grid. So remember, the way it works is that you start with all the digits, right? All the digits could go potentially into a square, and then you start to cross out and eliminate all the ones that already appear in the same row, column, or 3 by 3 square. So I'm doing this too. So for every position A, first of all, if there is already a number at that position, I don't care to calculate anything. I only need to figure out what can go into an empty square, in a square that's already full. I never need that, so I don't bother. And otherwise, what I do is I list all those positions that are conflicting with I. So all the indices that are in the same row, same column, same 3 by 3 square. And then I use this reduce operator of streams. I say start with all the digits, right? So we start with all 10 digits. And then for every position J, what you do is you remove the value that's in J from that set. So you start from the full set, and then you go over all the positions that conflict with I, and everything you find in those positions, you remove from the full set. At the end, what's left is what can still go into that position. Okay, so that's a little harder to read because of this reduce method. It's usually called fold. That's a fold left in lots of languages. Java calls it reduce. So it's a folding operation. That's another high order operation that streams implement. You can see you're passing it a function of 2 arguments here. One that I like better because it's much more readable. I also have a function to check if a grid is consistent. So I don't need that for solving because my solving approach does not introduce inconsistencies, but I use it in parsing input from files or from users. I don't want to start from a grid that has already conflicts. There's no point, it cannot be solved. So I have to check that the grid as we start is consistent. So I have an is consistent function that checks an array of values to see that there are no conflicts. This one I like because it's very interesting the way it's written with streams. So I take all the numbers I, all the indexes I, and I say for every I, either it's a 0, right? So if there's no number there, there is no problem. Or for every j that is a position conflicting with I, you get 2 different values. The value of j is not the value of I. That's what it means to be consistent, right? So for every non-zero value I have somewhere, for all the indices that are conflicting positions with this, I cannot have the same value. If you think of it in logic terms, right, this all match is a universal quantifier. So I'm really evaluating this. For every I between 0 and 80, either the value of I is 0, I'm happy, or for every j that conflicts with I, the values are different. That's how I would write it mathematically. This code looks very much like this formula, right? This, if you think of all match here as this universal quantifier, that's exactly the same thing we're doing here. It's often called for all, this operator in functional programming, the universal quantifier. Java, of course, has non-standard names for everything, so it's called all match. But that one is easier to read than the reduce. You can see how the logical expression of what it means to be consistent is transformed into code fairly nicely with the streams. Few other places where I use streams. So I can give users a stream of the values in the Sudoku, so they can do whatever they want without modifying my grid. They can just dig through that stream. And then I'm using that to check if a grid is complete. So if I want to know if a grid is full, I can do that with a stream. I can take the stream of values and then check that none of them match the condition to be equal to 0. Right, so all the values are non-zero. The grid is full. If I want to know how many numbers there are in the grid, so typically Sudoku grids, the good ones, they are as few numbers as possible while still keeping the unicity of the solution. That's the good ones that they like to do, right? Lots of empty spots, but it's still a unique solution. So you may be interested in seeing how many numbers are filled, because the lower the better. I can again take my stream of values, filter to keep only the non-zero, and then count how many I have. That gives me the number of values in my grid. What I want to emphasize with this is that this code is just as good as what you would do with loops, right? So in particular, this is going to stop the moment it finds a non-zero. So it is complete the moment it finds a 0, right? So we are looking at the numbers. The moment where I find a 0, I know the grid is not complete, I exit. Right? This, again, because the streams do lazy evaluation, they are not going to evaluate more than they need. So it's the same thing I would do with my loop, and then first 0 I see, do a return out of my loop. Right? So I'm not losing anything. Same thing here. This is not going to allocate a list of numbers and then count them. Right? So stream filter does not calculate anything. Only when I do count, it's going to start counting how many numbers are non-zero in that list. Okay? So I can achieve the same algorithms, I would say the same performance I would have with my imperative code. I can do that with streams. So I did end up using streams, but not for my main solving method for the reasons I've already explained. Those of you who know me may be wondering, what, no Scala? Usually there is some Scala in my talks. Of course there's going to be some Scala. It cannot be all Java. I know it's the Java users group, but still, I have to plug in some Scala. So of course there's going to be Scala because this all comes from a Scala program. So I use that as the programming assignments for my students, and we do that in Scala. So I have also a Scala implementation. I've done it in Scala many times. The way it started, I was curious to see, okay, so what I already do in Scala, how far can I go with Java? Right? Can I do everything I already do in Scala in Java? That's how I got started with this. So if we were to do that in Scala, a somewhat more modern language, what would change? So I could create, again, a private solving method that creates an iterator of solutions, right? Same approach. What changes is that the Scala iterators already have a flat map. So I don't have to implement my own. So I already have a flat map on the iterators, so I get that for free. Other than that, this is really the same code, right? You do an iterator of all the possible values, flat map, and then for each branch, the recursive call. So that's the same thing. Another thing that's interesting in Scala, if I wanted to keep all my solutions but not compute anything until I need them, instead of having a field that is null and then testing, oh, if it is still null, now it's time to initialize it, which is the typical pattern for delayed initialization in Java. Scala has something called lazy val. See, when we decide to be lazy, there are different ways of being lazy. This lazy val creates a field that's not initialized until the first time you touch it. So the first time you need it, the initialization takes place. Kotlin has the same mechanism. So I use that again for my my possibles and my old solutions. I use a lazy val instead of my field initially null and my if. The beauty of lazy val, by the way, is also thread safe, which my if approach is not, without a lock. This is another interesting thing of Scala. So if you remember in Java, I have a, actually I should go back to this Java. What I want to talk about is somewhere, way in the past. Another talk maybe. Where is this thing? So bear with me, I've lost it. Here. I'm looking at non-possibles, and I'm saying if it is non-null, I'm happy. I already have the possibles. And if it is null, then generate the possibles for me. Okay, so that's a way in Java to say if the thing is still null, calculate the value. You can see that what I pass to this require non-null else get is a lambda expression. Right? So I'm passing the code that will have to run if the thing is still null. It looks a little bit different in Scala. It's not super important, but that's part of the lazy evaluation theme. I have to go back and try to find it again. So in Scala, what I do, I store my non-possibles in an option instead of null, not null. And then the option as a get or else. Give me the value if it's there. If it's still empty, then calculate it. What's interesting to notice here is I'm passing this code here not as a lambda, but as a regular, as a normal expression. That's because get or else can take arguments lazily evaluated. Right? So I'm passing this argument without evaluating it, and then I will only evaluate it if this thing is still empty, as opposed to having to pass a lambda. Right? So there is even more lazy evaluation mechanisms in a language like Scala. One last, yes?
For the Java evaluation, that's one that you said that was not thread safe, or that was.
That's for this thing, for the lazy val. Right. So the Java I'm testing, if it is null, calculate it and assign it. Right. So that's not thread safe because two threads could test it null at the same time. Yeah, it doesn't. Yeah, you may still create it twice because you fail only on the cast of that. So typically use a lock or the double locking anti-pattern. You can do all sorts of things, but you have to work hard at it. Lazy val gives me that delayed initialization even in the presence of other threads. So if two threads try to access that for the first time, one is going to calculate it, the other is going to wait until it's done. Kotlin has the same mechanism. which is very useful. One last thing that has nothing to do with lazy evaluation, but that's a thing that's also does not exist in Java and is so extremely useful in a language like Scala. Even the students admit it. Is the notion of opaque types, which comes also from functional programming. You may notice I have a small int set type here, right? So in my Java implementation, there's just int. That's how I represent my sets, they are int. Here I have a small int set. So what is this small int set? It's a type that's different from integers at compile time, but it's integer at runtime. Think of it that way, right? So it's a type that's used by the compiler to make sure I don't pass an int when I want a set or a set when I want an int. There are two incompatible types. So if I pass an int where I'm supposed to pass a set, it's going to choke and not compile. Once compilation is done, this type is gone and it's just an int. At runtime, there's no overhead.
Kind of like duck typing in Groovy.
I don't know Groovy.
It's a type deck.
Well, Groovy, the thing is, if it looks like a duck and it quacks like a duck, it's a duck.
Yeah, that's not because I'm introducing incompatibility between types, which is what I want. I want to catch my errors. It is extremely useful if you start to have methods that take, say, a length and a temperature and a date, and they're all ints or double. It's easy to flip the arguments, right? You pass the temperature and the length, or the length and or the temperature. You never remember which is which. Here you introduce a type length, a type temperature, and you cannot make that mistake anymore. But at runtime, those types don't exist. Just regular doubles. The code that's being compiled is the code that takes plain doubles, or here plain ints. So you have the beauty of the type checking at compile time to avoid those mistakes without the runtime cost. I find this extremely useful.
What's that feature called, Jalen?
Opaque types. That's how it's called in Scala and in ML. Little story about this. I have another assignment, which is a mastermind solver. Here we do all sorts of little games like that. And in my mastermind solver, I have to generate all sorts of combinations, right? So it's huge data structure that you do, that's Knuth algorithm to solve it. So I want again to be compact. So I'm encoding, a pattern, a mastermind pattern with the colors as an int. I'm encoding a score as an int, and I'm encoding a pair pattern plus score also as an int. So I have three types: score, pattern, and score pattern, and they are all at runtime ints. So in Scala, it looks nice. I have three opaque types. I cannot make mistake, pass a score when I expect a pattern, or a pattern I expect a score. All of this is going to be caught by the compiler. And then at runtime, everything is just an int. I had a student who needed to do some extra work for honors. So I asked him to redo this in C and in Python, right? So he did it in Scala, redo the mastermind first in C and then in Python. And then he told me in C, it drove him nuts all the times he messed up his int. It's not hard bugs to solve. He felt it was wasting his time. Every time he was passing a score instead of a pattern instead of a score, mixing the order of the arguments, right? You have a function that takes two scores and one pattern, and that's all ints. He was always messing them up in C because everything was an int, right? You do a type def, okay, fine, everything is still an int at this point, so the compiler isn't going to catch it.
If he wrote tests, he would have found it real fast.
Huh?
If he wrote some tests, he would have found it real fast.
He was using my test, I suppose. And so then after his C implementation, he wrote his Python implementation, and he said, I don't want to run into the same problem. So in Python, he introduced three types: score, pattern, and score pattern, all little wrappers around an int. So now he gets his three different types. It's much cleaner. The IDE, especially IntelliJ, was telling him which types were what, but he has the runtime cost. Every int now has become an object. So in Scala, you get rid of the best of both worlds, right? You have the compile time checking without the runtime cost. So I mention it because it's really a feature I think it's nice to have when you have it in your language. Huh?
Does Kotlin have that?
So Kotlin is getting sidetracked. Kotlin is doing what Scala used to do. They have this notion of value classes. So you define a class that is labeled as a value class. So you still define your class, say small int set that contains an int. So you have a new type because you've defined a class. The compiler checks all those types. And then at runtime, it's going to try to erase that class completely and just replace all those things. So all the methods that take a small int set are going to replace with methods that takes an int, as long as it is possible. So for instance, you run into problems with generics, things like that, where you can put ints, but as much as possible, all those things will go. So it looks a bit different, but it's the same thing. You have it in Kotlin also. ML added, the functional languages added. Finally, and I think for once, probably on time, I can do it again then. My conclusions, or I can have more conclusions. I have more conclusions that are not on the slide. So in Java, you can have higher order functions and lazy evaluations. Another stream is the main one where you have all those higher order functions, map, filter, flat map, all those guys, but there are a few others optional. The options of Java have the standard higher order functions. You can do map, flat map on options, which is also very useful. They don't have it for collections or iterators. So if you want to do like square all the numbers in the list, you have to jump into the world of streams, do your higher order functions, and jump back into the world of lists if that's what you want. So that's different from, say, Kotlin or Scala, which tend to implement this directly in the collections. Streams, that's what I was thinking while doing this. You know, I was complaining a lot about streams and their iterators that don't work and so forth. But at the end of the day, streams were not created for that purpose, if you think about it. The idea was not to bring functional programming in Java. The idea was to handle large data efficiently, right? Streams have that capacity of running in parallel. Right? They can do map and apply the function using multi-threads, or do reduce, again, using multi-threads. So the beauty of the Java streams is that you can get those parallel streams that implement those higher order functions using multi-core processors. So that's really their goal, right? Large quantity of data processed with parallelism. That's why they are so complicated in some sense. It's not really to do functional programming, but they have been sort of used for that because Java doesn't have the functional programming higher order functions elsewhere. So if you want to do some functional programming patterns, you have to jump into the world of streams, and then you don't care too much that they can do parallelism or anything like this. They are not easily amenable to memorization as far as I can tell. So going through iterators doesn't work because the iterator has this do not use warning in its documentation. Streams have a whole bunch of low-level methods that have been recently introduced, but I think it's mostly to define customized collectors. I'm not sure they would help, but anyway, it was getting too complicated to dig into that. There may be a way to add memorization to the streams without going through iterators.
What about all the new gatherers and stuff that are there?
Right, those are the ones. It's more for collectors, I think, those gatherers. I don't think they would help me do memorization. I wish, I don't know, since we're at Oracle, aren't those guys managing Java? Maybe they should add a few higher order methods on iterators. I think iterators are very often what you need, right? Because you get the lazy evaluation, you create an iterator, nothing is calculated, you transform it, map, flat map, filter, whatever, and then you start digging from it. That's a pattern I use a lot in Scala. I wish Java iterators had.
We can't file it.
Sorry?
We can't file it.
Yeah. Let's add. Yeah, especially because the iterator stream doesn't work, right? Otherwise, you have a stream iterator, again, you're set, but no, it doesn't work. So that would be a simpler alternative to streams, not all the baggage that streams have by being pushed based, by handling concurrency and all that jazz. We don't need that half the time. And high order methods on iterators would make me happy. So yeah, let Oracle know that they can make me happy. The code, like I said, is on GitHub. So I have this Java code. If you want to have a closer look at a whole bunch of tests, but the tests are in Scala. Those are the tests I use for when I grade my students' code. So don't give the URL to students. They're not supposed to know what the tests are.
Well, they'll have it if they watch this talk on YouTube.
Yeah, they watch other things on YouTube, I'm sure. The book that someone won, you can also go back at this. This is the sort of things I discuss. I talk at length about lazy evaluation, chapter 12, not using Sudoku, but using the subset sum problem as an example. And in chapter 14, I implement trampolines, where I am being careful with implementing my flat map so I can nest it 100,000 times if I want to. My meta conclusion, which I didn't put on a slide because I never thought I'd reach my last slide anyway. But since we have a little bit of time, I was wondering, okay, so why does this matter, right? Why do we care about any of this thing I've been talking about for an hour? Usually my motivation, and that's what I use in class, that's also what I use in the book, is the little patterns, right? The map that squares the numbers and so forth. That's nice. Okay, that's cute. But once you start getting into real problems, you're gonna hit the point where that doesn't quite work, right? It's getting a little too complicated. It's a little more than just a little map and a little reduce. And maybe there's a fancy combination of higher order functions that you can use. Maybe you cannot see it. That's why I like to emphasize recursion to my students, because that's the fallback thing. When you're stuck, you may have to write a recursive function here and there. So I say that the nice little patterns, fine, until it gets complicated enough, it's good to understand more fundamentally. So for instance, In my case, I know that flat map is the fundamental operator. I know what I'm looking for. I just need a way to flat map iterators. I know if I have that, I'm going to be all set. I know what I'm looking for. I know what the signature of flat map is going to be. I know what I'm trying to implement. That's one reason. Second reason that I emphasize is when things go wrong and you have to start to debug these things, that can get a little nasty. So I'm a big fan of functional programming. I find it easier to read, like I said, not more difficult to write, but it can be a little hard to debug at times. You don't have good stack traces of what's happening in your computation. So when things go wrong and you have to start to dig under the hood, that's where I think knowing a little more than just the plain patterns of okay, little map to square numbers, little filter to remove empty strings, you want to know a little bit beyond that. And then because I promised I'd talk about AI, that's my third reason more recently is, I don't know, all those nice little patterns are so obvious. How long before the IDE starts writing them for you? I mean, you're going to make a living writing the next level, right? Not the little things. So if the patterns are so useful, so clear, so obvious, how many of them are going to be generated? And then your job is going to be to go to the next level, the ones that are not generated. So that's why I emphasize, a deeper understanding with some meat to it when I talk about functional programming, as opposed to, hey, I just use streams and the higher order functions and you're all set. So that's my meta conclusion.